Welcome back. So, today we will study the fourth lecture of Unit 1. In last lecture, we have studied the behavior of the channel, and in the case 1, and we have made it with two cases. And the case 1 is that where VGS is greater than VTH and Vs and VT equal to 0. And we have seen that the device is on, but but there is no current in the device, right? And in the case 2, we have seen that VGS is greater than VTH, that is threshold voltage, and Vs that is equal to 0, and but VD is now greater than 0 volts. So in this we have seen that voltage along the channel it increases, and the channel voltage varies with the local capacitance between source and drain. And we also observed that the charge and the voltage, okay, the charge and the voltage is very small in this, and the free electrons that accumulate in between the source and drain, unless and until if they have a voltage difference, then only the current conduction happen. As there is a like positive current, then the flow of ID is happened in the channel, and current will flow through the resistive path, right? These all we have studied in the behavior of the channel. That means we have seen here the actual charge carriers or actual charge that is takes place in the channel. Okay. So the next what we were trying to identify or to determine is that the current voltage characteristics of a MOSFET. So now the today's lecture, it will start with the current voltage characteristics of MOSFET. So before that, we will now again consider the same two what do you call the same two cases, right? We'll consider the same two cases and then we will move ahead. So as you know, yes, here we have the cross-sectional view of a NMOS transistor. So it is seen here like a metal gate or a polysilicon gate, the oxide thickness, then the substrate. And here it is also defined that, and we have also seen the dimensions, right? We have also seen the dimensions of the MOSFET in the previous lecture. So there we have defined the W, the L, what is W, the what is L, and also the oxide thickness, right? We have studied all those. But in this, the only thing is that the device engineers can or the circuit engineers can, while designing a layout for them, they can change the aspect ratio, that is W by L. But the oxide thickness cannot be changed, it is fixed, and that is taken from the library, that the foundry which they have given, right? So this is something we have seen, the simple cross-sectional view of a MOS transistor, right? So in that case, if we again consider in the case 1, the derivation in the derivation of an current voltage characteristics, the first is channel charge density. Okay, the channel charge density. So first thing we know that here we have also observed that yes, this is a channel, and we have seen the effective channel, because the channel it is no more or no longer we say that it is a length of the channel, because while implanting, when it get exposed to the thermal heating, then few of these diffusion atoms will move from here to here, and from drain to towards here and towards this. So therefore we have observed and we have seen that there is an effective length. But when it comes to the derivation of the current voltage characteristics, the first is that the channel charge density. So the how we have seen the charge, we have the capacitance and the voltage, and the charge density means, that means from here to here how much charge do I require, what is the voltage that is existing between this channel, as well as the what do you call, the quantity of the charge carriers that is existing. I mean, that means in the number. Okay, in within that means what? If suppose a electron is moving from source to drain, we need to identify how many electrons are moving, and how much charge does it have to move, and what is its voltage, in which voltage, with what voltage it is moving, as well as what is its velocity, and the interesting part is that within how much time. Okay, that means we will be calculating in the seconds. Okay, as of now, we will not be studying and we will not be taking one electron and then it is moving in the channel with this much of velocity and this much of charge within this time. Not that. But what we do, as if it is moving, here it is different, and here it is different means what? Here the charge would be different, or the electron, or if I can say the voltage, it will be different here, and here it is different because it has been given as 0 volt, and but here the VD is something greater than 0 volt. So as it moves, then it has to, the charge has to, I mean, the charge has to take or should have whatever the voltage that drain has. So in that way, we will be trying to find the channel charge density. So in this case, yes. So in this case, first is the case 1, right? The case 1, case 1, that is VG, that is VG is greater than VTH, comma, and VD equal to 0, right? So here we have seen that, sorry, VG equal to 0 and VG is greater than VTH and VD equal to 0. That means the device is on, right? The device is on, but no current, right? Right. So here we will be taking the channel charge, right? The let me write here the channel charge. So that is denoted by QCH, that is equal to capacitance into voltage, right? So this is like capacitance per unit area, what we say, right? We simply take that capacitance per unit area. And here the, right. So when I say this capacitance, we have observed that the complete capacitance, right? The complete capacitance, right? This is something gate VG. Yes, this is VG, VD, the VS, and plus, and plus. Right. So here we are saying like So here the channel charge, that is equal to CV, right? Capacitance and the voltage. So this capacitance is per unit area and it is given in coulomb. And here we have in this we will be considering the length, right? The length and the W of a the W, okay, the W, and that is the width of the gate, right? And then we will be taking the complete oxide capacitance, this one. Rather we say the thickness of the oxide, we take the complete oxide, total oxide capacitance. Okay, and then here we'll be having a overdrive voltage. Okay, a overdrive overdrive voltage. Okay, so here what I do, let me write this equation, that is W L COX, okay, VGS minus VTH, VGS minus VTH. So this is said as actually VGS minus VTH is said as overdrive voltage. This one is overdrive voltage. Okay, VGS minus VTH. If suppose in this case, if VGS is greater than VTH, then we'll be having a channel charge, right? If VG is greater than VTH, then we have a channel charge, right? We have a channel charge. Suppose if VGS is less than VT, then we'll be having only a depletion charge. If VG is less than VTH, then we'll be having a depletion charge. Okay, having a depletion charge. So here the total in this case, then QCH will be equal to 0. So in this case, QCH equal to 0. As we were calculating the channel charge when VGS is greater than VTH, then we have observed this equation with the overdrive voltage, right? So now the channel charge will begin if VGS is exceeding VTH, right? If it is exceeding thing, then the channel charge will start generating or start, it will start from here. Okay, it will start from here. Now, so now if I want to find charge along the channel, if suppose if I want to now find the charge along this channel, right? So what I do, then I'll be dividing this equation by L. Okay. So if I say like, if I say like when I divide this complete equation by L, then the for what purpose I'm doing this? I'm doing uh, I'm doing this like to find charge along the channel. Okay, to find or to observe, to find charge, to find charge along the channel, right? Along this complete channel, somewhere, or if I can say somewhere, to find or either I can find here or somewhere here or here, somewhere. Okay, I'm trying to find somewhere. So if I want to find charge along the channel, then I need to divide this equation. I need to divide this equation by L. So in that way, I'll be getting like QCH equal to QCH equal to WC WCOX, right? WCOX and VGS, sorry, VGS minus VTH, right? LL will get cancelled, so VGS minus VTH. So now when I say L, when I say L, because I am trying to find charge along the channel, that means L. So it may be in meters, right? Right? This may be in meters. So now the complete charge, this complete charge will be in coulombs per meter. Okay, coulombs per meter, because it is in the length. It is in the length, and this we have find along the channel, right? So it will be in meters. And the previous thing we saw, it is a simply coulomb. This is simply coulomb. Okay. Here what we did, we have only observed the channel charge, but this is channel charge along the length. So this is what we got, the two equations. So next is in case 2, we have observed that in both the cases we saw like in one case there is no current and in another case we have current, as because we have applied drain greater than 0 voltage, right? So now in case 2, let me change my pen color. In case 2, uh, let me tell like VGS is now greater than VTH, right? And now my VD is also greater than 0 volt. Let me put a 0 volt. Okay. So now you know that in this case, voltage along the channel will increase. The voltage. Okay. The uh, the voltage along channel increases in this case, right? And now suppose as we know, suppose if I draw again a transistor, because all the time we will be defining the transistor, right? So this is my oxide and this is my gate, right? And showing this is my substrate. Okay, VG, VD and the VS, right? In this, as you know, this is my channel, right? So here what I'll be doing in this, we will be trying to observe voltage. Suppose I have a carrier somewhere, right? My carrier, the or the electrons are has to move from somewhere from here to here. Once it is moving from here to here, here to here, here to, the voltage will be different, right? Here, obviously, just a minute, my pen is not working. Yeah, right. Okay, yeah. So here, just a minute. Right. Okay. So my voltage, if I take a electron, my voltage is different from here, 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 somewhere, right? So suppose if I take a mid somewhere here, okay, I want to take somewhere here, then I'll put it V of X. Okay, I'll put it V of X, right? Because here it is obviously 0, and if I move here, then this voltage will be more than this. If I move here my electron, then obviously this electron voltage will be different from here. So from here this will be different. If I move here from here, it will be different. Then if I do like that, but at the end, if I come, suppose if I'm assuming my VD equal to 1 volt, then obviously my electron should have the voltage of 1 volt. But as of that, we are taking a mid of something like V of X. It is an assumption thing. Okay, so now if I want to write my channel charge density, okay, channel, this is channel, and I'm writing density, okay. So then it will be something WCOX VGS minus VTH, right, minus V of X, right. So this is what we saw if I assume a mid somewhere some voltage. But is it that is our task to find only the channel density? Our objective is to find the drain current as a function of VGS and VDS, right? Our objective is to find drain current. That is, it may be with respect to VGS and it can be with respect to VDS, right? So here we simply saw the charge, the channel charge, right, with the length as well as with the voltage. So what changes do we find? We are taking the means we are observing the no, we are identifying the charges, means the electrons that move from source to drain, and it within what time, right? Rather I say time, the voltage, okay, as well as the length, okay. So that we have observed in case 1 and case 2, but our objective is to find the drain current, okay. So let me, so here what we said, like we are supposed to uh, derive or to determine the IV characteristics. Uh, so students, can you people tell me or just think of this, like how can we change the IV characteristics? Here I could tell you we have the input and output characteristics. Here we have input and output characteristics. It is a thing like you are supposed to tell me what are input characteristics, and which voltage and which current will be varying, okay, depending on which voltage the current will vary and what has to be constant, and what are the output, means what is input characteristics and what is output characteristics, with what the both currents will be varying. Both currents means here it is very clear that drain current, ID is drain current, okay. So this drain current can be determined by both, that is input and the output characteristic. So how can this drain current with what voltages it has a possible ways to vary, okay, that is the question. So I'll give you 60 seconds, think of it, and we will be back again. Okay. So yes, uh, so here one thing is very clear that we will be varying, sorry, we will be, we will be identifying or we will be plotting current characteristics, right? Current voltage characteristics. So input characteristics are nothing but ID that is vary with respective to VGS, and output characteristics is said as with respective to VDS. In this case, yeah, this is output and this is input. So in these both, suppose I'm plotting what do you call VGS, right? If I'm plotting VGS, that means my VD is varying, right? My VD is varying here, and here my VGS is varying. So input characteristics, simply we draw something like this. This is input and these are my output characteristics. So here these are input characteristics and these are output characteristics, and here with different gate voltages. Suppose gate voltage is suppose this is VGS equal to 0, like 1, 2 volt, like that. It keeps on varying. And this is VD versus ID, and here it is VGS versus ID. Okay. So here at a time both the characteristics we cannot plot, but this is different and these are different. Okay. So this is how we will try to calculate, or we will try to plot the characteristics of input and output. And coming to that, the next we will be studying about the ID, ID, ID and sorry, VG, sorry, uh, ID and VGS characteristics. Okay, right. So in this point, in this, so now this is drain current. Okay, drain current, that is ID, and from the semiconductor physics, uh, we have seen that we have doped and we apply electric field, and we have obtained a current with the, again we have with applied electric field the carriers will reach to the certain velocity, like that we have seen. From the physics what we have observed, like we observed like with the doping, and the electric field is generated and therefore the current is obtained, and then this electric field will the carriers in that electric field will reach us to a certain velocity. So now the velocity is defined by mu and E, right? The mobility is higher for electrons than holes. This mu is the mobility. Okay, this is the mobility. So in drain current, in order to means first we are studying the drain current with velocity, right? With velocity, but from the physics, we have doped, right? We have doped. Doping is done. Then with the doping, we have a diffusion current, right? Diffusion current. Then we also have electric field, and therefore we will in that electric field the carriers will reach to the and the carriers in this electric field will reach to the certain velocity, right? This is what we have observed in the semiconductor physics, right? Now, so as we said that this is a velocity, okay, this is velocity, this is mu, and this is electric field. Okay, this is electric field. With the doped, there is a diffusion current, and without a thing, with applied voltages, we may have a drift current, right? So that we have seen. So now, in this, the mobility will be higher in the electrons than the holes. So here, the electric field equal to the minus dV by dx. Okay, this equation is we got it from the physics. Okay, this equation. This equation we got it from the physics, right? So now the velocity equal to something like v equal to mu, right? This minus dv by dx, right? At some point in semiconductor, uh, sorry, at some point in the semiconductor, will be measuring certain velocity for the carriers, and also will measure the derivative voltage with respect to distance at that point. Okay, suppose I have again a semiconductor device, the MOS device, right? MOS device. So what we are doing at some point, some point I'll be calculating some velocity, right? And will be deriving the distance, right? At some point I'll take the velocity and the derivative I'll take it with respect to the distance, that is the voltage. Okay, so that we have, this will be minus. Okay, minus mu dv by dx. So now if charge is moving with the velocity, suppose if the charge, whatever the charge, that is q, right? The q, whatever the charge in this field, the charge that is moving with the velocity, that is v, in the channel, the electrons are moving with velocity v in that way, right? The charge is moving as well as the electrons is also moving with the velocity in that path, in this path, right? Whatever the charge that is existing and whatever the electrons that is available in that charge area, so those are moving with the velocity in this area or in this path. Okay, then then in this length uh, the velocity and how much is the charge, Okay, what is the charge that we have? Okay, what is the charge that we have? We will be observing in this, right? So the total charge is something like, let me write here, Q charge density, Q charge density equal to, that is V dot WCOX and VGS minus VTH minus of V of X. This was the equation where we took, right? So here in this we took a point, right? We took somewhere within that length. In that length, somewhere we have observed some velocity. Means we can consider along this channel one velocity that we have defined here. Velocity. Make sure the notation of the velocity somewhere I'm writing like this. But if I write like this is something of voltage. Okay, so V dot, that is V cross, or this is width and the total capacitance of the oxide, then VGS, VTH and V of X, right? This we have observed. Then the means now again the total charge passing through this, the total charge, whatever the total charge that is passing through this or interfaces in 1 second, that is actually defined as current. Current means what? Current is what? That is total charge that is passing within a second. Because somewhere if I observe, suppose if I say sorry, I'm taking somewhere here the velocity. Okay, let me. Okay, let me draw. Okay, somewhere if I'm moving here at this part, I'm taking this velocity. Okay, this velocity is this. Okay, then rest all is the equation what we have observed in the previous. Okay, and how we can define current? That is the total charge that is passing through this. The total charge that is passing through this interface in a second, right? That is about that. So here we have seen the current. Okay, so now let me write an equation for the id equal to v, that is velocity, q charge, charge channel, okay, density, okay, equal to v velocity w cox, right, vgs minus vth minus v of x, right? So this is due to the electrons moving from right to left, we have a positive charge from left to right. Okay, as these electrons are moving from right to left, a positive charge will be a positive charge will be left to right. Okay, so now as these electrons are moving from right to left, okay, again the electrons are moving from right to left, so it will be a negative. Electrons is negative, right? So the next step is that then I'll write my ID. Sorry, equal to minus velocity, then q channel charge density. Okay, channel charge density, that is equal to minus velocity, right? Vgs minus Vth minus V of x, right? So this negative from where we got? We got from due to the electrons moving from right to left. Therefore, the charge, positive charge will be having from left to right. Okay. So with this equation, okay, now multiply and integrate both sides with x. Okay, now multiply and integrate both sides with x. In this, then we will have id equal to, velocity is what? Mu into electric field, right? So this minus, it will become plus, and mu, that is n. If I'm writing n, that is n type or Donar, if I can say like that. And then electric field I have defined like dv by dx, then wcox vgs minus vth minus v of x, right? So I have given the velocity term, I have written here velocity term, making it from minus to plus, and then sorry, velocity equal to mu into electric field, that term I have included here. So now after now we are supposed to multiply and integrate with x, right? If I do that, I need to integrate id and dx, and that is equal to, I'm taking the constants mu n w c o x, I'm taking it outside, and then I'm integrating the vgs minus vth minus v of x to dv, right? So I need to know the limits, right? I need to know the limits. So if I again take a MOS device, then if I take a MOS device, right? So one thing, this ID, the current is up to where? From here to here, right? From here to here. This is something I can say like L, right? This here the current is 0, and here the current is something of L. So I'll take the limits from 0 to L, right? Because the current here, electrons are moving from left to right, sorry, right to left, current is generated, and from 0 to L, that I'm taking. And coming to this integration, uh, we may know that this is with respect to voltage, and this is with respect to current. So now the voltage here, it is here the voltage is 0, and here the voltage is something VDS, right? It is 0, and here it is VDS. So 0 to VDS, right? Now I got the limits, now I got the equation, and now I need to integrate it, right? When I do integration, then I'll be having something like L, sorry, ID equal to sorry, mu n c ox w, then VGS minus VTH into sorry, V minus 1 by 2 V square, right? And this is the from 0 to VDS, okay, from 0 to VDS. So it is, if it is like that, then again I'm supposed to divide the equation, by L. Okay, divide the equation by L. If I do that, L, sorry, it divide the equation. So if I do that, then I'll be having LID, sorry, LID mu n c o x w. Okay, then I'm just solving this. VGS minus VTH, right? V minus 1 by 2 V square, sorry, 1 by 2 VDS square, ds square. So if I divide it, then I'll be having only ID equal to mu n c o x w by L, right? W by L V VGS minus VTH, okay, into VDS minus 1 by 2 VDS square, right? But if I divide it by L, so if I divide it by L, this L will get cancelled, and then I have included this. So this term is nothing but second order term. Second order term. So this is how we will calculate, this is how we will draw the, we have derived the equation for drain current. Okay. In the next class, we will be studying about whether is this drain current is satisfying that Vg is less than Vth, or the Vg is greater than Vth. This equation satisfy with what? That we will be looking into the next lecture. Okay, thank you.